Hello, and welcome to EDA Summit 2023. My name is Rob Tomkins. I'm a Principal Core Product Manager here at Solace. And today I'm going to be taking you through scaling microservices in event-driven architectures, the power of non-exclusive and partitioned queues. So if you've got an event-driven architecture, you probably already know that an enterprise has a lot of different moving components in it with a lot of different technologies that need to be mapped and work together in near real time. And an event mesh is an effective way of doing exactly that. Now, one of the many types of technologies applied with event-driven architecture is the microservices architecture. And that's because it delivers on the promise of fully decoupled environments with the ability to provide massive scale. Now, part of these different microservice consumer scalability instances is that you have different consumers and different producers working with different capacities and different loads at different times, resulting in scalability concerns. And today we see customers addressing those concerns through kind of three different approaches. One approach is really over provisioning and setting up your environment and your configuration to handle that peak load. It means you have to keep on working to expand your event mesh to that peak load, but it's relatively hands-off compared to some of the other options like manual scaling, where you dynamically set up new brokers, consumers, and producers through human intervention when the need arises. A little bit more complicated, but perhaps the most effective is to use automated scaling that detects when a queue or a consumer is getting overloaded and dynamically scales up the number of instances to handle that kind of scaling requirement. So, what are the challenges of scaling these microservices? So it's more than just spinning things up and spinning things down. You need to think about it in the context of an event-driven architecture. So you probably want all the messages to be guaranteed message delivered. And in some cases, you want to ensure in order delivery, particularly when they hold some sort of context. You don't want to receive a modification to an order before you received the request to create that order, for example. You want to make sure there's consumer resilience. Sometimes network things happen or with the consumer environment and then consumer goes down. And you need to be able to dynamically adapt to that from an event-driven messaging standpoint. You need to have the load balancing. You need to adapt to the number of instances that are of that microservice that are in place and handle slow consumers when they occur. You also need to factor in the challenge of routing. You want messages to go where they should be and not in places where they shouldn't. You need to be able to filter so that the consumer only gets the messages it needs and it's not dropping messages that it shouldn't have received. And last but not least, you need to be able to handle this auto-scaling factor I just talked about, where you want to really dynamically scale your environment in a hands-off manner. An approach like auto-scaling is highly desirable. So you may have many of these challenges based on your particular use case. Now, key to event-driven architecture's ability to handle the scalability of microservices is the queue. When you look at the producer provides topic, the topics subscribed to by a queue. So the producer basically decides which queues are getting the message. But once it gets to the queue, it's up to the queue which consumer receives that particular event. And so it's critical that we kind of drill down on the queue in this question. So how do you scale a microservice with queues? Well, there's a number of different queuing solutions out there today, and I'm going to focus on two different categories, exclusive and non-exclusive, and then within the category of non-exclusive, competing consumer and partition queues. Now, an exclusive queue does a one-to-one mapping of a queue to an active consumer. Any additional consumers that are added on are really alternate consumers and only in place in case the original active one fails. And then they become the active one until they fail. So it provides the ability to be resilient to consumer failure. It does provide in-order delivery, but scaling here is really just limited to vertical scale by context. So you could add manually more exclusive queues, and that works nice if you've got limited context. But for the bulk of microservice implementations, we see a need for auto load balancing and sometimes the need to auto scaling, especially as microservices evolve to become really dynamic. So that's where non-exclusive queues enter in. And there's really two different types of non-exclusive queues that we support. There's one type called competing consumer, which is really perfect when you've got a context-free application. So you're doing something like translating event from one format to a different type of message. A competing consumer totally makes sense there in that you can handle a really large load with a competing consumer. And I'll go into a bit more detail about how that works shortly. And then the second type of non-exclusive queue is a partition queue. And this is really where you've got some stateful data set. You want to do some context mapping and ensure that because that consumer is maintaining state, that you're getting an in-order delivery for that particular state. As I said before, if you're receiving an order, you want the creation of that order to come before the modification request for that order. And we'll cover off how partition queues work and do that. So non-exclusive queues with competing consumer type, the way they work is really with a round robin delivery that's normalized to handle slow consumers. So it takes the number of consumers that are bound to the queue, and it does a round robin delivery of each message against each, parallel processing them one message to each consumer that is currently active. One disappears, it gets factored out of that round robin, and its message, if it wasn't acknowledged, gets sent to a new consumer. Now, this nature of if a consumer disappears or knacks a message and disappears, it going to a different consumer means that at times in-order delivery is not guaranteed. But this works really well if you're looking at stateless applications like I talked about before. And this also supports auto-scaling. So if you take, for example, KEDA, which is a common approach to auto-scaling, Kubernetes event-driven auto-scaling, and it takes feedback from the queue, says, hey, this queue is getting full. It sends a message to generate the Kubernetes environment and the consumer itself. That consumer comes up, binds to the queue, and it becomes a new active consumer. And similarly, if it tears down, it can gracefully disconnect from the queue and free up those resources. So a little bit more about KEDA. So KEDA, as I said, was Kubernetes event-driven autoscaler. It really allows you to designate an external trigger, whether on a queue or consumer or some other dashboard, and that determines object scale and how many objects should be spun up, spun down at a given moment, and does the environment set up to do exactly that. Now, this is a topic that could take well over half an hour to cover. So I've provided some information about KEDA itself, but what's key about KEDA is just that it brings up an instance of that consumer. You can use whatever sort of auto-scaling technology you want, as long as it brings up the application, it binds to the queue. Our non-exclusive queue capabilities will be able to handle it. So the next category is fairly new, around partition queues. And this is where we take non-exclusive queuing to the next level, in that it provides context management with in-order delivery. And it auto scales itself, allowing you to have a large number of contexts, a large number of consumers, and delivering in order for each context while maintaining all that load balancing and auto scaling of non-exclusive queuing. So how do I know I want to do a partition queue? Well, if you have a variable application load, so take, for example, flights, can be pretty quiet at night, but pretty busy at 9 in the morning, and then again at 6 o'clock at night. Well, that's a great example of a variable application load. So you may want to spin up and down your resources to handle that. If you have a need for dynamic consumer scaling as a result, absolutely, that's a capability that partition queues is designed to address. But last and not least is that your consumers have a stateful data set. If you're keeping track of all the luggage or the passengers for a flight, and at different points you're getting different messages about that baggage or that traveler, you will likely want all that information in a single consumer. Maybe you don't care which consumer it goes to first, but all future messages about that bag or that passenger should go to the exact same consumer. And that's a real sign that what you're looking to do is something with partition queues when you have that stateful data set. So how does this work? So we're providing the load balancing and context awareness all in one. And the way we do that is add a little feature to our APIs, which allows you to add a key. And this key goes into the partition queue and is hashed. And you can look at a hash function as basically kind of like a random number generator with a seed that is basically the key that goes into it. And so you get this kind of random number out of it, but if it ever sees that same key again, it will provide the exact same value. Now we take the value from the hash function and we apply a modulus against the number of partitions that you have configured with that partition queue. In this case, you can see an example with 6 partitions. Now, each partition is mapped one-to-one to a consumer. So each partition has one consumer. We've got 3 consumers, so that means each consumer is going to get 2 partitions like this. But we've also got the ability to do the auto scaling. So you take statistics from the consumers or the queue itself, feed that in, it can spin up a new consumer if it notices it's congested. And that consumer add will bind to the partition queue. It will go through a 5-second hold down to make sure that consumer is up for good and stable. And then it will map partitions to it. And because we've got 6 partitions and now 4 consumers, you'll have 2 consumers with 2 partitions and 2 consumers with a single partition. And here you saw this link from partition 4 moved from consumer 1 to consumer 4. Now, there's also some really unusual advantages around partition queues. First of all, it's the only technology in the industry that provides filtering and in-order delivery and consumer scaling all in one. And it's doing this with a really intelligent, fast consumer rebalancing system for really dynamic scaling. And it's unique in that the number of partitions is application specific. So it's really centered around what does your application require as opposed to what does the infrastructure require. So let's step back for a second here and talk about the key. So a key is really the context, and it's contained within a 255 byte structure or less. And it can be a combination of anything. It could be order, transaction, flight. I've lifted off a number of examples here, but it really needs to match the use case and the data set. And this can be very dynamic. You can have keys that last 3 seconds or 3 days. It's designed to be dynamic. And through the hash function, it's just dynamically mapped. It doesn't really matter to the broker what is in that context. It's just whether that context is different from what it's seen before or not. And it really benefits you to do it where you have a numerous number of orders or transactions. The bigger the number, the more random and the more natural of a distribution of your load against the partitions you'll have. But it's not totally necessary to begin with. Now, one thing I get back from customers and colleagues is, isn't this a lot like Kafka? Well, in a way, it really is Solace's answer to Kafka consumer groups, but there are considerable number of differences. So one thing to note is the use of the terminology of topic between the two. When you look at a Kafka topic, it really is sort of like a Solace queue more than a Solace topic. It really is, what contains the partitions in this case, like a partition queue contains partitions. So you can't look at a Kafka topic and think it's a Solace topic. They're kind of different. And actually, a Solace topic is really about the filtering. And in Kafka, you usually have to do that at the consumer or the stream processor. Here, Solace can do it right at the broker, right at the edge of the event-driven mesh. Partition queues are, similar to Kafka consumer groups, and they, allow you to scale up, different applications having a new copy of the messages that came in from a particular topic. So you can have different consumer groups consume from the same topic. In Solace, what we're doing is you would just set up a different partition queue that subscribes to the exact same topics within Solace. So that allows you to dynamically decide how many partitions you want by application, not by topic. And that provides a lot of flexibility. It also means that the rebalancing is really by per application and not by topic. So it really allows you to customize based on application. But when you look at the internals, they're actually kind of similar in that partition is mapped to one-to-one to a consumer, just like in Kafka. And in Kafka, they can use KEDA to spin things up. So can we or any other autoscaling technology, as discussed. So when you really want to get into a comparison between the two, there are some differences. Here, a partition queue is application scope, whereas Kafka is really a set of partitions per topic. Filtering is subscription-based, whereas Kafka is more this coarse topic-based approach. The partition queue is context-aware, just like Kafka, and it provides in-order delivery and high performance, whereas in Kafka, there is actually a trade-off between performance and in-order delivery that Solace doesn't have. With a partition queue, it's all centralized to a broker. All partitions are on the same broker. You provision a partition queue on a broker. It's all there. In Kafka, a partition is a set of partitions is native to a topic, and they could be anywhere in a cluster, which actually makes it a bit more complicated to run and manage. And with Solace, we provide an intelligent rebalancing capability. Kafka provides a couple of options. There's an eager stop the world option that is really dramatic and causes a big pause for everything around rebalancing. They've also got a incremental cooperative rebalancing, which is a bit more dynamic, a bit less optimized, but faster. We can outperform that with our intelligent rebalancing. In addition, we've got more flexible partition resizing. In either case, changing the number of partitions is not something you want to do frequently, but we've got some options to make it easier. So, to make partition queues look more clear to you and to understand better how they work, we've prepared a demonstration of partition queues. Okay, here we are in PubSub Plus Manager on a brand new broker, default VPN, queue dialog, and let's create a queue. And let's give it a name, Partitioned, for lack of a better name. And in the Edit Queue Settings dialog, well, it's collect non-exclusive. You'll notice it comes up with options for partition count. There's also some advanced settings you can use. One is for rebalance delay, which is how long it waits after the number of consumers has changed to see if it stabilizes. And then there's a rebalance max handoff time, which is once a rebalance is started, it gives you that period of time for the old consumers to consume the pre-rebalance messages. You'll see this in the demonstration. So let's apply 12 partitions to this queue and apply the changes. And here we go. All right, next we need to set a subscription. We'll go with test/star because I love Solus wildcards, and away we go. All right, to visualize this, we're going to use pub/sub plus playground. So here's pub/sub plus playground. And up here is the event generator. The event generator is going to generate events with 8 different colors. Each of these colors is mapped to a key, and they're going to be published on topic test/1. So they should be consumed by our partitioned queue. And then we have 4 different consumers that once the event has been generated and sent to the broker here, they'll come out of the broker to one of these consumers. And you can see, looking at the configuration for these consumers, that they're bound to that queue named partitioned. So let's send one event out, and you'll see how this works. It goes to the broker. The broker has sent it to consumer number 1. And let's generate a few more events and see how this all kind of maps from queues to consumer. And you can see that different colors are landing in different buckets. Now, this is not done in a round robin fashion. As it's hashed, it's basically a random number generator that ensures each key of the same color will land in the same bucket, but you don't get to know what color is going to end up in what bucket. If I reran this demonstration, they could land in completely separate colors, buckets. All right, so let's pause it for a second here so it doesn't overflow. What I'm going to do next is do a little example of how this works when you change the number of consumers and that rebalance that occurs. So let's start the streaming up, and I'm going to turn off this one since it's got so many different keys, and put it back on really quickly. And what you see is it waits for 5 seconds from when I turn that off, that rebalance delay. And since it came back and it was in the exact same state after 5 seconds, it just continued to have the same partitions that it owned before. And the messages just continue to flow as if nothing had really happened. And this is great if you have kind of, a network event or something that's short term that might cause disruption. We don't want to rebalance everything. But let's say you had something more serious. You actually decided you wanted to turn down one of the consumers because, hey, it's not busy enough. So let's send those messages out, turn this off. And you'll notice after about 5 seconds, the messages will start being sent to a completely different partition. So you can see here, yellow is being sent to this 4th one, and blue and black are being sent to the 2nd one. And this is recurrence of rebalance. After a rebalance occurs, there is that drain time where it keeps trying to send the old messages to the previous consumer mapping. If it doesn't get drained in that time, then it automatically flows into the other partition. So let's try seeing what happens if you add a consumer. So let's turn this one back on. The broker will have forgotten it because it exceeded that max hold down timer, and you'll see it's going to get assigned a completely different set of keys because it's been assigned different partitions. So here you can see the red balls are coming in. All right, so that's my demonstration of partition queues. Okay, you saw in that demonstration that partition queues are an effective way of maintaining context and providing in-order delivery within each context in a way that it dynamically adapts to the number of consumers that are being mapped to that partition queue. But to sum it all up, let's look at how non-exclusive queues and their 2 different types can really help with the challenges we outlined earlier for integrating scalable microservices with event-driven architectures. So once you've got a non-exclusive queue, you've already got a number of different challenges resolved. You've got guaranteed messaging in place. You've got consumer resilience in place. You've got the load balancing. You've got the routing solved, the filtering solved. The auto scaling is inherent in what we've done from non-exclusive queuing. So those are all resolved. The choice between competing consumer and partition really boils down to, is it stateless or stateful? Is in-order delivery critical or not? And there's a little bit of difference in how they handle slow consumers. With a competing consumer, it's got a natural ability to dynamically offload slow consumers by adding more load to other consumers. With partition queue, you're actually mapping, you're going to add consumers to offload more and more partitions from consumers to allow them to speed up and take load off them, which is a little more complicated. But it boils really down to stateless and with message order not ensured, or do you really need to track that stateful data set inside that microservice instance? So it really boils down to is what's in your use case and what is in that consumer instance, and does it require that stateful data set tracking? So there you have it, folks. We've got a wide variety of different capabilities between non-exclusive queuing with competing consumer and partition queues to let you map the needs of your microservice instance to the queuing type of your event-driven architecture to successfully deliver highly scalable, context-free or context-full messaging between your microservice instances. Thank you for listening.